Okay, so we can begin, I guess. So Atul, do you want to introduce me, or should I just begin? I think. Okay, so hi everybody, welcome to the special functions and number theory seminar. The topic is the partition-frequency enumeration matrix, and this is joint work with Hartosh Singh Bal, who is also in the audience. Okay, so what are we enumerating, and what is this partition frequency enumeration matrix? So we begin with a very simple matrix. So this matrix has, you can see that it has ones in the first row, then 0, 1, 0, 1, 0, 1, then 0, 0, 1, 0, 0, 1, and so on. So in the ith row, basically, there is a 1 if I divides j in the jth column. So this is the thing, and it's 0 otherwise. So it's a number theoretic matrix. And we set up a sequence of equations. So we chop, so an is you take n columns and n rows, and then there's some sequences which form p0 to pn minus 1 and f1n and so on. And there is one additional condition which is required. So let me just try start from here. So we assume p0 is 1. Okay, and we take n equal to 1, so that's just a 1 matrix. Then times p0, that's 1, and on this side I will get f1 1. And if I multiply this matrix, I'll get 1. So I get f1 1 is 1, and then I use this equation to find p1. So I know p0. Now I find p1 from here. So k times fk, and you're summing. So it's just 1 times f1 is 1 times p1. So this gives me p1 is equal to 1. So I start with here. Then the next one, I have p0 as 1, p1 is 1 from here. And now the matrix that I'm looking at is this one. And again, I multiply. So I get 2 at the top and then 1 here. And this is f1 2 and f2 2. And again, I use this equation. So 1 times the first guy, which is 1 times 2 plus 2 times the second guy. And it should be 2 times p2. And this will give me p2 equal to 2. And now I have 1, 1, and 2. Now 3 by 3 matrix. So the matrix is formed by chopping it off up till n columns and n rows. Okay, so I hope the process is clear. So first I get 2 plus 1 plus 1, that's 4, then 1, and then 1. And this is again f1 3 now, f1, f2 3, and f3 3. And now I use this guy to find that 1 times 4 plus 2 times 1 plus 3 times 1 should be equal to 3 times p3. So that gives me p3 equal to 3. And if we carry on like this, so I think you got the idea. If we carry on like this, I get the following sequence. So it's 1, 1, 2, 3, and 5, 7, 11, 15, 22, 30, and so on. So this is the sequence. This is the sequence of partitions. So this is the sequence of partitions of M. And it's very, very, very interesting and strange. And somehow we didn't find this matrix or this approach to enumerate partitions anywhere in the literature. In fact, this matrix, we couldn't find much of it. So there are similar matrices which are there, but we couldn't find it. So in any case, let me show you how to do what are partitions. So partitions are unordered sums which add up to a particular number, and we use a particular, we use a symbol UK to list partitions. Okay, somebody's wants to come in. What we use is we use this symbol U1. So we use these symbols U1, U2, UK, so on, to list partitions. And this is somewhat non-standard. This is something which Hartosh and I have been doing. So let me show you what we are doing. So what we do is, so for n equal to 0, there's an empty partition. So it will be clear what a partition is shortly. For n equal to 1, we take U1 as a partition. So U1 simply stands for 1. So U1 stands for 1. So UK stands for K. And for n equal to 2, we add U1 to this guy, and we take a new symbol U2. So now this stands for 2 times 1. So this stands for 1 plus 1. And this is a new partition 2 of 2. And I'll just keep adding the numbers. You take 1 as P0. So this is Pn, the number of partitions. And there's 1 here and there are 2 here. So when n equal to 3, I take any partition of 2 and add U1 to it, and I'll get a partition of 3. So 3 U1, U1 plus U2. And then I add a U2, U3 as a partition. So there are 3 of these here. So again, this one is 1 plus 1 plus 1 plus 1. This one is 1 plus 2. And this one is 3. So unordered sum of numbers is called a partition. And similarly, let's do n equal to 4. So you add 4 U1, 2 U1 plus U2, U1 plus U3. And now you add U2 to U2. So you go back 2 steps and you can add and get some partition and U5. So here you have 5 partitions. Okay, so the point is that we are using this symbol to denote partitions. UK stands for the kth part, and FK stands for the frequency of k's, number of k's which come. And the point is that if you replace UK by K, then K times FK, if you sum it, that becomes N. So that's what it means for it to be a partition of N. And this FK is a frequency of K. So it hasn't played much of a role in partition theory, but we found it useful. So this is called a frequency of K. And if you take this is the frequency function, you sum all the frequencies. So this means that lambda is a partition of n. Fk lambda, the sum over all the lambda, is the sum of all the frequencies of lambda. So you take, for example, f1 of 3, you take 3 times 1 and plus 1, 4. These two things add up to the frequency in 3. And you can do f2 and f3 and so on. And it's clear that if you sum this, if you multiply this by k and then sum over all the lambda, all the k, then you will get n times Pn. So n comes from each guy, and then Pn comes from the sum over all the lambdas. So this is clear. This is also clear. This is a recurrence relation. What am I doing here? I'm saying the number of partitions, number of k's, the frequencies, the number of k's which come in the partitions of n. So each time I'm getting a partition of n, I get, and it has a k in it, I can basically get it by adding uk. So I add uk to a partition of n minus k. So this is a partition of n minus k. And if I do that, I get a partition of n with a k in it. So this becomes, this is a clear recurrence relation for the sum of the frequencies function. Okay, so we are interested in the partition frequency enumeration. So this frequencies and partitions are enumerated together, and these frequencies in the case of partitions have a combinatorial meaning. So that's why we call it the partition frequency thing. And now let me say, so this is clear, because if we add UK to a partition of n minus k, I get a partition of n. And then from here, it's I can find the matrix. So F1n is, for example, Pn minus 1 plus F1n minus 1. And then that is Pn minus 1 plus Pn minus 2 plus so on, Pn minus 3. Similarly, F2n is Pn minus 2 plus F2n minus 2, which will be Pn minus 4 plus Pn minus 6, and so on. So Fkn will be Pn minus k plus Pn minus 2k plus so on. So it's clear, we get this matrix equation. So on the right hand side, you'll get 1 ones, and then 0 1 0 1, so on. And here you are getting P0 up till Pn. And on the left hand side, you're getting F1n, F2n, and so on, Fn. So, so what I've done is I have shown that partitions actually satisfy this set of equations. And from here, it should be clear that they determine partition. So it's, I mean, this set of matrix equations and these two things together determines Pn and F1n. So there's a connection, clear connection. So we call this the partition frequency enumeration matrix. I mean, it's a new name that we have given. What is interesting to us is that this matrix is a very number theoretic matrix. So what is the number theory? What is the connection with number theory? And for that, let me give you an example. So this is Ramanujan's recurrence relation. Sigma 1n is the sum of divisors of n. This recurrence relation has been credited variously to Ford, and I found it in Ramanujan's notebooks in the books edited by Bernd. But Bernd himself has once mentioned it came in Euler. So I'm not sure whether it's known to Euler, but probably, I mean, it's possible, of course, Euler got it, but Euler got another recurrence for partitions. So it's possible he didn't bother. So,
Gaurav, you know which Ford is it?
Which Ford meaning?
I mean, initials. So.
I can tell you right away.
Okay.
WB.
Oh, Walter B. Ford.
This is 1930s. So, Edos used this identity to prove something, to get the first term in the asymptotic expansion. It's a very famous paper by Edos, and then Andrews has followed up on that. Anyway, so this is easy to prove. I mean, it was easy otherwise too. But here's how we prove it. If you look at it, I take that matrix and I multiply it by 1. So the matrix I had, I multiply by 1, 2, 3 up till n. So I get the first row by 1, second, 2, 3, so on. And here I get 1, 2 up till n. And if I sum all these guys, then I get sum Fkn, which is nPn. So this sum is right here. And this is the column sum. So if I multiply this matrix by this guy, this by this guy, this by this guy, and then sum over columns, each column will be this. So you can see over here it's 1 and 2. So sigma 1 of 2 terms are there, and you'll get with 1 you'll get with both of them you'll get P of n minus 2. Right. So it's a column sum kind of thing. So if you just sum the columns, you will get this part. So this is the, I would say, from the column sum of the left, on the left. And then you sum over all the columns and you get this result. So this is really, I mean, it just drops out immediately thanks to the structure of the matrix. And this is the guts of our thought process. Actually, we are done here, except I have a million examples. What we do is we show enumeration of all kinds of partition type objects. We find a calculus to find the PFE matrices. So we call them partition frequency enumeration, or PFE, and we give a lot of examples to show how number theoretic results come out, and then some further applications. And again, many are known, but there are some new stuff also which we came out through the study. So what do I mean by partition type generating functions? So this is an experiment of giving a part, partly home presentation and partly, Blackboard talk. So I hope you don't mind, but this is what we call a partition type generating function. So a general generating function with a z which captures the number of parts, and a bk. And if here bk is could be a it could be a complex number, so it need not be a combinatorial object, but we still call it a partition type generating function, and whatever we get here we call it a partition. So this is a generalized partition, and we can calculate a partition and a frequency function formally. So these things have combinatorial meaning when bk's are integers, but if bk is not an integer, it need not have a combinatorial. Still, the many of the results are basically combinatorial. And in this case, when we calculated the matrix, it came out very similar to the PFE matrix. So if you look at it, these B1s come here in the first row, B2s in the second row, and the Z's come in power, z square, z cube, 3 raised to 4, and then z square, z cube, and so on. So very, very similar matrix, extremely similar to all these partition type functions. So this is step one of our calculus. We will, keep calculating more and more PFE matrix. So just a quick example. Partitions with all parts distinct. Now, how do you generate them? You generate them by doing 1 plus q raised per k going from 1 to infinity. So here z is equal to -1, and all the bk's are also equal to -1. And this is what the frequency relation boils down to in this case. And the matrix is again very similar. It is the same matrix but with alternating signs. So this is 1 and so and 0, 0, 1, 0, 0, minus 1. So one can enumerate distinct partitions exactly the same way, except this is the partition. What happens when all parts are odd? So here I'm only taking partition. So for example, I can't do 2 plus 3. I can do 1 plus 3 as a partition, but this is not allowed because all. So what happens is all the frequencies, when we do frequency, all the even frequencies are 0. So alternate terms are 0. So the matrix is essentially the even rows are all 0. So again, we start with P0 to Pn minus 1, and the alternate terms happen to be 0. The even frequencies are 0. So in general, this works with any partition function. If you're taking parts in a particular set, you put those rows, you make them 0, and that's it. And then you generate everything. So almost everything is covered by just this partition function, but there is one or two new sets of partitions which require something like this. So this is our calculus step 2. Here we take the product of two partition type partition generating functions, and when we calculate the partition frequency matrix, we can represent it in two ways. One way is just to take the partition with B's and with C's and just add them together. And that's this. And the other way is that we take a row from here and a row from here and then put it together. So again, very, very similar to the previous guy, but this is a very useful thing. So let me give you an example of over partitions. Okay, please feel free to interrupt me in case something is wrong or if I'm missing something. So what are over partitions? Over partitions are they were introduced by Ortiz and Lovejoy, and they were introduced in 2014. And what they are is that one of the parts, exactly one of the parts, can be overlined. So it's a special part. So you can have 2 plus 3 plus 1 plus 1 plus, well, 3 usually comes first. And let's say this is 2. One of the 2's you can overline. One of the 1's you can overline. But you can't do 2 of them. So how do we make them using our symbols? We use 2 symbols. And once you see the symbols, then it will become clear what these are actually. So we use 2 symbols, U and V. U is the ordinary partitions, and V are the partitions with distinct parts. So V represents the overlined parts which are distinct here, and these are the ordinary. So this partition is broken into 2 parts. One is this and one is this. And this guy is represented by V, this guy is represented by U. And this chap has got distinct parts. So, what do? We list the partitions in distinct parts in reverse order. So when n is 4, for example, I'm starting with 0 partition, it's in blend empty, and these are the ordinary partitions. U1, 1 plus U1 plus U1, that's 2 U1, U2. Then add U1 to each of these, insert a U3, and so on. And similarly, I do partitions of n minus m into distinct parts. So I can't do U1 plus U1. So V1 plus V1 is not allowed. So I just have a V1, V2 here. I can do V1 plus V2 here, and then a new one, V3, and so on. And then I just add them together. So, for example, 2U1 plus V2 represents 1 plus 1 plus 2 overlap. So I just add these 2 guys up. And that's it. And here we have 2 frequency functions. One, the ordinary type, one for distinct parts, and a similar kind of thing. And the matrix looks like this. So you put a matrix for the ordinary partitions, and you put a matrix for distinct partitions. Or you can add the 2 and do it, and then you will get P0 up till Pn minus 1 here, and here there are bars, let's say, and then here you'll get frequency. So this is this will be a 2n by n matrix. So you will get frequencies for both the parts. You can add up a frequency function both for u's and for v's. So in particular, this shows that any type of partition functions that you have, you can use this matrix to get more insights into it. Okay, and this is the connection with the number theory thing. So remember what we did in Ramanujan's case, we multiplied by 1, 2, up till n with the PFE matrix. So this was P0 to Pn minus 1. And then I got 1 times F1 and 2 times F2 and so on. What we do here is we multiply by any arithmetic function, F1, F2, Fn. And any arithmetic function. So this is the sum I get over here. So F1, F1n, F2, F2n, and so on. So the sum I get is this one. And then the column sums give me this one where GK is defined as this is the sum of columns. And from here to here, I'm just taking generating function. So note that this is a convolution of two functions. So you can take generating function, then you get a product of. And in the important case where Fk is equal to K, then we get these general results. So now this is for any B. You see, earlier these were all one for partitions, but now you got for any B and any arithmetic function. So any arithmetic function F and any B, and you can mess with it and get different kinds of things. So I should mention that if B's are K, if B of D is equal to D, then you get partitions, plane partitions. You get something equivalent to plane partitions. So you get similar results for plane partitions too. So there's nothing special about which partition function you're taking, nor about the arithmetic function. That's the point. So here's an example. I take one from my elementary number theory book, mu of n. And this is a well-known identity. Summation mu of b is 1. And if I just plug it in over there, this is what I get. So the frequency function is very, very related to the Mobius mu function. So this is the Mobius function, or the mu function. I'm not, I'm not familiar with where, I haven't seen this identity anywhere. This could be new. This is quite easy, but you never know. It might be somewhere, but we haven't seen it in the usual. As I said, FK does not play much of a role in partition theory. There is a set of results where it shows up, which I'll talk about later, but otherwise it doesn't show up. Okay, the first recurrence of this kind, now we are taking a partition function of another kind. So this is q infinity, which I have not defined. So aq infinity is 1 minus a, 1 minus aq, 1 minus aq square, and so on. And this can be viewed as a formal power series or as an analytic function if absolute value of q is less than 1. So this was considered by Euler, and what Euler did was he calculated the coefficients of 1 minus q square, and so on, and he found that there were large number of them were 0, and this was the famous pentagonal number theorem. So the coefficients En of this Q expansion are 0 unless n is k times 3k plus 1 or 3k minus 1. And in that case, it is a minus 1 raised per k. So that's Euler's pentagonal number theorem. So I use these as the partition function, my capital P, and then I get a identity, a recurrence relation for the sigma function, and this is due to Euler. So this is this was probably the first result where some kind of connection. These numbers came in a partition function. This is 1 over q infinity is the generating function for partitions. So these numbers are very linked with partition, the pentagonal numbers, and Euler was quite excited about this result. Let me show you what he said. So this is Euler's comments. I'll just leave it for a second so that you can read it. So I should mention this guy, Jordan Bell. He has translated many works of Euler, and it's very useful to see the translations. So and he's also written some papers in this area. So you can see Euler is excited, and it's not just Euler. Ramanujan, Lemmer, Eval, um, all these people, and maybe a few more whom I'm missing, they have similar results. And I think the main reason why these kind of results are useful is because they help you compute. So they compute small numbers. It's very easy to compute small numbers using this recurrence relation. I mean, by hand. So once you have this kind of recurrence relation, you can calculate the numbers very fast. So you see, this is a very sparse set. A lot of numbers are zero here, right? So it's a very quick recursion. So it's in computer science lingo, it's order n square. So here's an example from Evil, which is much more complicated, but this also fits into our scenario very easily. Our proof is very, very similar to what I've just shown you. Here we use something else, maybe Jacobi's identity, and we get a recurrence relation. So if n is of this form, a triangular number, then there is this non-zero right-hand side. Otherwise, it's so this is using a theta product that Evil did it, and we also did it. And this is a new one which we found. I think it's new, maybe new. So a lot of things we found we feel are new because we haven't seen them anywhere, but they're relatively easy to get. So one never knows if something like this is there. So, but this type of recurrence, I mean, for two of them are known, but not this one for sure. Okay, so going back to the calculus, so we now essentially what we know is that there is this PFE matrix for products and products of products, and then each and from it some number theoretic results follow, some recurrences follow very quickly. This is what we know, and now we expand the story and say, what about series? So I'm giving a series of this form. Can I find the matrix? And the answer is yes, and the matrix looks very much like this. So the same matrix essentially, uh, and so Pn is any sequence, and we start with 1 again. P0 is 1. Then there's a unique sequence Bn and an associated frequency function which satisfies this. Now, this frequency function has not been studied for anything except partition. So it's entirely a new universe for us to explore for anything other than partitions, for sure. And anyway, so this is what it is. Let me do an example. So I start with the sequence. The sequence is the set of partitions with the property that um, so this will illustrate how it works. So this is the property that the difference between parts is at least 2. Okay, so distinct partitions are those with difference between parts. The minimum difference between parts is 1. Here the minimum difference between parts is 2. I mean, it's very natural. So Euler looked at distinct partitions with distinct parts, and Ramanujan looked at this. So this RR stands for Rogers and Ramanujan. And this is my I think I have repeatedly given talks on how to discover the RR identities, and also the same thing has been done by Andrews many times. So his Andrews number theory book had the first one which I saw in my undergrad. So anyway, so what we do is we want to find B1 such that this happens, and I know that 1 times F1 is equal to 1 times P1. And this is P0, this is P1. I know P's, okay? So I know this guy. So I know this chap is 1, and this means that B1 is 1. Okay, let me do another one. So suppose I know B1 is 1, and this is 2B2, and F1 2, and F2 2. No, I know. What am I doing? this is P0, which is 1 and 1, and this should be equal to F1 of 2 and F2 of 2. So one of them is easy to find. The first one I get immediately 2. This should be 2 times 2. So the second one I don't know. Second one I'll get 2b2. And then from this equation I will get, if I sum these guys, so 2 plus 2b2, it should be equal to 2 times p2. So what is p2? What is p2 is this guy 1. So this gives me b2 equal to 0. Let me do one more or two more. Okay, how far I've reached? Okay, I think I have enough. So I know ones now. I know b2, and this is 3b3, and I know 111. So this is equal to p0 3b3, and this is equal to f1 3, 2 f2 3, 3 f3 3. And I also know that the sum of these guys, so 3 plus 0 plus 3b3 is 3 times p3, and this is p3 is 1. So again, b3 is equal to 0. So well, you've got the idea. If you have a sequence, I can calculate all of these, and once I calculate them, I actually see that the sequence I get is sequence of b's that I get is 1 0 0 1 0 1 0 0 1 0 1 and so on. And I see that bk is 1 if k is congruent to 1 or 4 mod 5 and 0 otherwise. And if you assume that this pattern continues, then the matrix is the same as that corresponding to this product, 1 over. So here the product is basically, remember, 1 over q to the k is for bk. So bk, when bk is 1 or 4 mod 5, then we have something, otherwise there's nothing there. And this generates partitions congruent to 1 or 4 mod 5. So, so what we started with partitions with difference of parts at least 2, and we get to partitions with the parts congruent to 1 or 4 mod 5, and this shows that we can discover the Rogers-Ramanujan. So, I'll comment on this. This gives an idea actually of where this theorem fits into our place. But let me say that there is another fourth step. Suppose I have this guy. Suppose I have this chap. I have a GK, any sequence which satisfies some recurrence relation of this kind. Then too I can find the P's and the F's and the B's. So I started with products. I have product of products. Then I have sums. And now I say any sequence which is this arithmetic sequence which I'm interested in, I'll be able to find the P's for which this arithmetic kind of relation works. So, you know, this Ramanujan type relation, you say, I want a Ramanujan type relation for this sequence in Sloan's list of sequences. You know, he has nearly infinite sequences. And you can find it using our thing. You can find what is the partition function. Then see, is there some kind of combinatorial story which is happening over there, and so on. So this is very easy to do. We use some Mobius inversion to calculate. So we define BD by this equation, Gn, and then we use Mobius inversion, and we get the matrix. And once we get the matrix, we get P's and the F's. So, so that's the fourth step of the calculus. Now, what we saw was that, so there are 4 steps: products, product of products, then sums, then any column sum. We call Gn was the column sum. So if you're given a column sum, that's fine. And we saw that we started. So there's a connection with an algorithm called Euler's algorithm. We saw that we started with a sum. Here's a sum, and we could get a product out of it. So Andrews gave a algorithm for this. It's called Euler's algorithm. I don't know why it's called Euler's algorithm, but I've seen it in Andrews' books from his books on theories of partition, and which was in 1976. Maybe Euler used some of this technique somehow, and this is how Andrews uses it, and these follow from our. So this follows from ours, and then if we plug it in, this also follows from our scenario. So Andrews used this equation to find the BKs. It's been implemented by Garwan and Maple, and then by n number of people. What I noticed this time I mean, I've read this thing from Andrews' book. He has a 10 lectures book. So this was in his 10 lectures book, which was very famous. It's a white book, and he only talks about when BKs and PNs are integers. But we have used this algorithm for anything. I mean, they could be polynomials for all you care. So this is actually I think some level of enhanced understanding of how one can use Euler's algorithm, which comes from considering the matrices. Okay, so here is a one in honor of Atul's new chair. So Atul got a chair by a gift by students, and I don't know if you can. It's a zeta function. So it's been there's been some 3D printing which has happened. So it's a very nice chair for him, and we start with the product of sine pi z over pi z, and this is the product, and we know that this is from the power series. The right hand side is from the power series. Expansion of sine pi z over pi z. So what I want to do is I want to show you how to write a matrix for this product. So first of all, take one term of the product, 1 minus z square of k square, and for this the PFE matrix is easy. It's a row matrix. And then I can take m of these products, so k going from 1 to m, and then whatever the partition function I get a m cross n matrix, because I can put the rows one on top of the other by my second step. And then I do what are the terms in this matrix and what is the column sum. So the column sums are these 1 over k raised per 2n for k going from 1 to m. So this relation is the Ramanujan type relation. And now if I take m going to infinity, I immediately get gmn is the zeta function. So I immediately get this recurrence relation for zeta function. So we were very excited when we got this, but then we found that it is a rediscovery. It's not as well known. I mean, I think it's a beautiful formula. It should be there on Wikipedia, but somehow it's not so well known. I've never seen this formula. It's a very trivial formula. And just think, what happens when n equal to 1? When n is 1, then you get zeta of 2. This term is k going from 1 to 0 vanishes. And this term you get just n equal to 1. So you get pi square over 6. So this is Euler's famous solution to Bessel problem. And this entire thing does not include Bernoulli numbers, but it's not anything which Euler couldn't have got. I mean, this is very simple elementary stuff whichever we got. So anyway, from here, recall that we also had something to go from sums. So when you go from sums, you get this strange identity. I again don't know what it's good for, but you can write another product for sine pi z over z, and here the exponents are involve the zeta function. So I mean, I didn't I didn't define this. Zeta of no, I did define it. So just for even numbers, we got something over here. Okay, I can do the same with any product. So here I'm taking a Jacobi triple product identity, and again this product over here is a triple product, and what this means is, so q square infinity. So that's 1 over q square, 1 minus q raised power 4, 1 minus q raised power 6, so on. Then this guy is 1 plus zq, 1 plus zq cubed, 1 plus zq to the 5, and so on. So the base is q square, and there are 3 of them. And the third one is 1 plus q over z, 1 plus q cubed over z, and so on. So this triple product is equal to this sum. This is known as Jacobi's triple product identity. I can do the same thing, and we're just doing it in one special case here. I just put z equal to 1. Whatever I got, those gk's and so on, gives rise to this recurrence relation. So this very interesting set of recurrence relations for sigma. One is for when sigma 1 is when it's odd, and one when it's even. So we got another recurrence relation for the sigma function. So again, this seems to be new. And all right, so okay, now we come to some applications. So these applications are, we take powers of generating function. So you take any generating function q and take its power, and then let this be the coefficient. Now, this is r could be anything. R could be a complex number, and we generally take p0 to be equal to 1, and q over here, and then it works out very nice. So we get a general recurrence relation for powers PR and PS, and it seems that S equal to 1 is a case which was well known and rediscovered many times. So after we uploaded the paper on arXiv, then I got an email from Alan Sokol, who said that he's seen something like this, which is he sent me a reference. Turns out that S equal to 1 case is well known, and Gold has applied it in many cases. And we had some applications when S was not equal to 1. This is a general formula which we've got. I think it's 76. I'm not sure if it's 74 or 76. Okay, so if we apply it to sums of squares and triangular numbers, so I'm using Ramanujan's notation again. So one side theme in my work is to try and find, easy proofs of Ramanujan's results. So Ramanujan uses this phi and psi. Phi is the generating function for squares, and psi is the generating function for triangular numbers. And if you raise it to the kth power, you get the generating function for the sums of squares and sums of triangular numbers. So the coefficient will be number of ways of writing n as a sum of k triangular numbers, and it's an ordered sum. So in case of partitions, it was an unordered sum. Now it's an ordered sum, and similarly for squares. So kth powers over here. And then we found the recurrence relations for Rk. Again, we thought this had been discovered, but this was known. This is in this guy. There's a very nice book by Kenneth Williams. So we don't know who it's due to, but Williams has proved it using Liouville's methods. It's there in a Russian book too, and this is a possibility that either Liouville got it on his own, or Ouspensky studied Liouville's work first. So it's possible that this may be known. But anyway, it was known. It's a very nice, elegant recurrence relation for calculating the sums of squares. All the information is here. You can just calculate everything. Same thing for triangular numbers. This we can't find in the literature, so probably it's new. So as you can see, it's in terms of triangular numbers too. So I don't know if somebody's seen it. Please let me know. It's again one of those results which we found. Sometimes we feel this must be known. So it's too simple and elegant not to be known. And this also we found it hard to find, but finally it was there in some standard. So there's a very nice book by Williams called Number Theory in the Spirit of Louisville, which is a copy of Number Theory in the Spirit of Ramanujan by Bruce Byrne, the title at least. But it's a very nice book. Okay, so applying this to powers of the theta function, again we found some results. So we had a PR and a PS. So we had a PR and a PS. So if one of these guys is known very, very well, then we can get some nice recurrence relation. So in this case, we have R equal to 1. And in this case, or S equal to 1 rather. And this case, we had S equal to minus 1. So if you take S equal to -1, then we can use this result due to Jacobi. This is a classic result. QQ infinity is the same thing which I showed you, raised power 3. It can be written like this, but this is spoiling the look. So let me update it. So maybe I can highlight it here. And this particular result is due to Lemmer. It's there in one of Lemmer's papers. In fact, I couldn't find the paper, but I found a math review which had this result. So this was used by Lemmer, and like I said, another set of people have discovered it. The combinatorics people in gold had discovered it in another context. But this particular result, where he uses this Jacobi result, so when S is -3, you can use Jacobi's thing to get a recurrence relation. And it's a generalization of Ramanujan's tau function. So Ramanujan had a recurrence relation for the tau function. So Ramanujan's tau function. So let me say that this, if you have one, let me use another color. So if you have QQ infinity and you raise it to the 24th power, then that gives you tau of n+1. So when R is equal to -24, then it gives you this guy, which is there. It's one of the published results in Ramanujan's. It's a famous paper on some arithmetical functions, on an arithmetical function. Okay, as a final application, let me prove some congruences. So Ramanujan, this is a famous story. Ramanujan noted, so McMahon created a table of partition numbers from 1 to 200, and Ramanujan looked at it and said that every fifth guy is divisible by 5. So 0, 1, 2, 3, 4. So P of 5m plus 4 is congruent to 0 mod 5, and then he found a very similar result for the tau function. And in fact, this one follows from this one. And these are all explained in Byrne's book that I mentioned. Number Theory in the Spirit of Ramanujan. It's a very sweet book, must read. What we found was that this could be embedded in an infinite set of recurrences, congruences. PR 5m plus 4 is congruent to 0 mod 4 if R is congruent to 1. So to remind you, PR is again QQ raised per R. Now R is anything. I mean, R need not be a number. It could be a rational number. So let me prove it. Going by the principle that everything should have one proof, where I have several proofs, but this is one result which we used, which we got. This is Lemmer's result. and n PRN is the sum over all these guys. Now, what I look at look at this sum. I look at each term of the sum. So for j congruent to 4 and 5 mod 5, it's something times something which is PR of, again, this is congruent to 4 mod 5. So by induction, and it's a smaller number, by induction this is 0. So it's an inductive proof. So when j is 4, when this j index is 4 or 5 mod 5, then it's 0. If j is 3, 2 or 1, again, you can simplify everything. And it turns out that when r is equal to 1 mod 5, then this term becomes 0, this is 0, and this is 0. So in fact, we can have a, you can just solve it. You can solve for r, depending on different kinds of, different. If you can generalize this to k, and then solve for r. So it turns out. So this is a really simple. I mean, it's one of the simplest proofs of this of these congruences for sure. It falls out immediately by looking at term by term. I don't know any other recurrence where this happens. All the proofs involves modular forms, this, that stuff. They're also not I mean, they're also elementary, but this requires Jacobi, Jacobi's result, and some, R matrices, some elementary manipulation. Okay, so I have in fact several infinite families. So this is the one which we showed. So when r is equal to 1 and minus 24, then we get Ramanujan's result. But we have r congruent to 4, 2, and different PR. So these are infinite sets of congruences. R can be a rational number. Now it's very recent work, Chan. So this is Hengwat Chan. We were talking about Chan and Wang recently. Hengwat Chan and his student Wang, who is now a professor in China, and he's agreed to give a talk in our seminar too. In 2019, they wrote a very interesting paper where they found and proved many congruences where this R was a rational number. So powers of the eta function they considered, they proved many congruences. They found many more. There were some conjectures there. And 7 of their congruences are included in this set. So they've got mod 7, mod this. They did a thorough search. It's a fantastic paper. And it's opened up a new area. But we've 7 of their congruences are, so they don't have infinite families of congruences. So we certainly have more number as such, but 7 of their congruences have been placed in some infinite family of them. And similarly, we have a mod 3 result, which is not there. It's not available. Mod 3 is not available. I'll just take one more minute. So we have a very similar result for mod 3, where powers of the eta function. Okay, some more things I haven't mentioned. If you don't mind, I'll take one more minute. So we have considered powers of power series. We also can consider roots of power series, in which case we get some results which are similar to Henninger, Reines, and Sloan. Some more recurrence relations, PFE matrices, and so on. I mentioned that this doesn't show up that much. FK doesn't show up that much in the theory of partitions. In fact, the only place where it shows up is what are called the Stanley-Elder theorems, and recently they have been found in work of Fine. And we have another paper on that, which came up on arXiv on the same day. And we have another set of congruences for the sigma function, which is coming soon to a short note. Okay, so thank you very much. That's all I have for you. Thank you for your patience.
Thank you very much, Gaurav. It was a very nice talk. So we start from something really elementary, and you were able to get so many new things. It was really great. So frequency matrix is really interesting. I mean, the way it is constructed. And you have congruences of different types coming in. You're saying the more ones that.
Well, more we have some congruences for sigma function. So again, one of these recurrences give this kind of term by term congruence, and that should be out this weekend. It's a short note. It would have been out by now, but I was preparing for this talk.
So, are there any questions for Gaurav?
I have a question, Arvind here. Hi, it's nice talk. So, do you have anything interesting to say about this partition frequency things for plane partitions?
Yeah. So let me just share it again for a second.
Huh.
So I mean, there's a lot of interesting stuff which we haven't sort of figured out yet, and hope to do. But let me just say that. Now let me look at this partition function, and I take, let's say, I take bk equal to k.
Yeah.
And z equal to 1. So this is a partition where kth part comes in k colors.
Yes.
And these are plane partitions. But I mean, your level of formulas, I don't know. I mean, they don't have such generating functions, right? I mean,
No, wait. So the fact that in bk equals k, I mean, also enumerates plane partition. I don't think there's a direct bijective correspondence between saying kth part contains k colors and plane partition. These are not, I think, not in bijective correspondence.
No, but I think there's a bijection. It's just a complicated bijection. So.
Oh, there is? Okay.
Yeah, I mean, but it's not. So the properties of this, how they transfer there, I mean, one doesn't.
Okay. But I see. So here you are not interpreting them as plane partitions, rather as partitions where the kth part has k.
Yeah, and here that g function turns out to be sigma 2. And but that's the result in McDonald. I mean, McDonald gets it too. So there's another story. I mean, we can do some symmetric functions too, but not all. I mean, we can't do existing ones. So this is a hope for the future that we can do some, few functions.
Yeah. So yeah, that's a good point. So if you can see what happens to Cauchy's identity or something.
Yeah. That's a little bit beyond. I mean, I think it can be done, but we haven't done it yet.
Okay.
I mean, if we do it for Cauchy, then that would be a big problem. So I've mentioned this to Hartosh that I really would like to have some way of, writing down a McDonald polynomial without.
No, but McDonald is higher up. I mean, even if you can get sure functions, that would be
so, yeah. I mean, sure function, at least you can write it down, right? I mean, without any.
Yeah, right. No, the original Cauchy identity is for sure function. So even if you can get that.
Yeah, so that we haven't reached there yet.
Okay.
Any other questions?
Yeah, I should stop recording at least.